Hello, everybody. We'll get started on lecture 13. What I want to do here is I'm going to cover a section of chapter 5 for us in Shangle and Bowles' Engineering Thermodynamics text. This is a section that is not not on any exam. But it's a nice little kind of review piece for to try to tie. We've talked about first law for closed stationary systems. We talked about first law for steady flow control volumes. And it's a nice piece that kind of puts the two together in a way. But this is unsteady flow. Right? Unsteady flow. We've been talking about steady flow and control volumes. When that DDT term goes to zero, what do we do when it's not zero? And that's really kind of our focus. This is not going to show up on an exam. In class, a lot of times we kind of hit this point where we've got I'm trying to give students a day or two to kind of get caught up and time to actually work through the homework. This is a nice section in the textbook, and again, it's not bad to talk about. It's just not something I'm going to test you on, but doesn't mean we can't talk a little about it. Exam two is coming up for my students. Check Canvas if you're trying to follow along and you're not taking my class, but you're using these videos to help you with another class. Normally, after you get done with kind of chapter 4 or 5 material like we are, normally you probably will be ready for an exam. So just be aware of that. Again, my students, more information on that, watch Canvas and you'll be caught up. And as always, email me if you have questions. Okay. Now, here's where we're at. Unsteady flow. Talking about unsteady flow. What does this mean? We've introduced when we talked about the idea of steady flow. I said, and I always use the idea of a garden hose on a hot day. When you first turn that garden hose on, if it's a long, 50 foot, 25 to 50 foot garden hose and it's sitting out in the sun, there's a period of time where when you first turn the faucet on, you run to the other end and you pick up the hose and there's not water coming out. Right? There's a period of time where you have more mass going into that garden hose than what's coming out of it. So there's a period of time where the mass of your system, if I call my garden hose the system, the mass of that system is changing. It's filling up, if you will. Okay, so there's a period of time where the mass in is greater than the mass out. And then I always talk about if you've ever done this on a hot summer day where that garden hose has been sitting out in the sun all day and you turn that water on and you go put your thumb on your thumb on the end of the garden hose at the other end, that hot water coming out might burn your thumb. Don't do that. Let it flow for a little bit because there's a period of time where the garden hose itself is at a very high energy state. It's sat out in the sun for a long period of time. So the energy of the mass going in is going to be lower than the energy of the mass coming out, and basically what that means is the energy of the system for a period of time is changing. It's cooling down. That cold water flowing through is going to cool the garden hose itself, the system down to a lower energy state. So there's a period of time where delta E system is going to be non-zero. So there's either a warm up or a cool down period for all devices. If they're not at steady flow, they're going to be unsteady flow. Okay, so but a lot of times we say, well, it's a warm up period. I'm trying to warm it up to or fill it up to a point where it can operate at steady flow, or maybe I'm cooling it down to try to get it down to a point of equilibrium. Those are kind of the main two scenarios, and there's quite a few things we can point to that you probably experience in a real life scenario that would be a perfectly good example of an unsteady flow system. But the thing is these are situations where they're only going to operate in an unsteady state for a very specific period of time. I always say that you got three options. If you're operating with an unsteady situation, there's three options. One is you're going to reach a steady flow scenario. You're going to reach an equilibrium. So you're basically warming up to or cooling down to that equilibrium point. So that's one. Two is it's going to exhaust, right? So if we if we blow up a balloon and then we let that balloon go, well, as we let it go, now that balloon is losing mass. It's pushing mass out of that balloon as it flies around. And so some of that energy as it's leaving is also going to cause a change in momentum of the balloon. And that's fluid mechanics we could get into. And that's approaching rocket science, honestly, but that's okay. Um, we'll leave that for later discussions, not in this class. But that's an example of an unsteady flow scenario. So again, it's either going to reach equilibrium and hold steady flow. It's going to exhaust out. It's like the balloon. Once we let it go, it's just going to go and then it's going to stop. It's going to exhaust itself out, and then it reaches an equilibrium, basically. Um, the third scenario is it blows up. Simple, right? And you can see this with the balloon. If you leave a balloon and you blow up a balloon too much, well, it's just going to pop. If we've got a turbine in a power plant and we keep feeding it higher pressure steam, higher pressure steam, higher pressure steam, to where we reach the limits of what that turbine can operate at, it's just going to blow up and throw aluminum shards of fan blades everywhere. And that's not good. And hopefully nobody dies as a result of that. I'm not kidding when I tell you in our line of work, units can kill people. It's not an over. I'm not being dramatic. It's not hyperbole. Um, that's why we label our units on everything. We always double and triple check our units. I digress. So those are three options, right? It's either going to reach an equilibrium, reach a steady flow state. It's going to exhaust itself out, which is two and one are kind of the same thing, or it's going to blow itself up. Those are your three options for an unsteady flow situation. Okay. So again, lots of examples we can point to. But if you look at the mathematics of it, we go back to the original form of the first law and the original form of conservation of mass. And the implications here is always for steady flow, we would say that ddt goes to zero, right? So when I go in minus out equals change, I just have in minus out equals zero because the change for the system over time is zero in a steady flow scenario. These are unsteady flow. The change with respect to time is no longer constant, or I'm sorry, the change with respect to time is no longer zero. The energy of the system is no longer constant. The mass of the system is no longer constant. We have a situation where at least one of those is not constant, and probably both. So let's look at that. Okay. So what do we do there? Well, there is a simplification we can employ. And it's a very simple simplification. And it's the most common thing we could do is we could assume what we call uniform flow. Uniform flow means that basically we're going to assume that the amount of mass, or basically the mass flow rate, if you will, the rate at which mass leaves, we'll assume that's constant. Okay. We could also assume that the properties, well, I guess the change in the energy is over a short period of time is it's constant. So it's changing at a constant rate. So mass is leaving at a constant rate and the energy is changing at a constant rate. And also, we could assume that the properties, either into or out of the system, are constant. Now, if you think about the garden hose we talked about earlier, if I turn the water on and I let it start running, at first, the water coming out is going to be really, really hot. And then over a long enough period of time, it's going to cool down. Okay. But if I just look at a few seconds when I first turn that water on, for a few seconds, it's going to be really hot. So if I look at for just the first couple of seconds over a very short period of time, then I could probably assume uniform flow for those first couple of seconds. And then maybe seconds 2 through 5, maybe I can make another uniform flow assumption where the energy change is pretty constant for that period of time. So I can kind of break it up into portions sometimes uniform flow. But the other way, maybe this one makes sense. This is also another one I like to talk about in class is if you know the aerosol cans that you spray and it sprays out a gas and use that to blow dust off of electronics and surfaces and things like that, right? Electronic cleaner gas, compressed air, a lot of people call it. It's really not actually air, but that's another story. Some sort of a fluorocarbon a lot of times, similar to a refrigerant. Anyway, if you hold one of those cans open for a long period of time, and here's what I would ask my class, what happens if I just take one of those aerosol cans and I hold it open for a long period of time? What happens to it? And somebody will say, well, it gets cold, right? Yeah, it's as the material inside expands to fill the vacuum created by material leaving, the remaining material inside expands. Remember, as something expands, that's work out. It's going to a lower energy state. It has to do work to expand into the remaining space. As it expands, it reaches a lower energy state. After a long enough period of time, a lot of that stuff will actually liquefy. So if you hold it open too long and don't touch the bottom of that can, because it can get super cold and actually don't do this. I'm telling you, do not do this. But if you watch videos of other people doing this in a safe manner, if you put on nice gloves and you turn that can upside down after you sprayed it for a long period of time, liquid will actually start spraying out. And that liquid is very cold. It will burn skin. Again, I'm telling you, don't do these things. Watch other people do it safely. But if you were to, and I always make the joke in class, if you were to take one of those cans, spray it for a long period of time, and then turn it over and start spraying that cold liquid out. And you could spray it on, I don't know, a lock or something that you own that lock. Only do this to things that you own. You own a lock, and you get that lock really, really cold, and you can hit it with a hammer really hard, and that lock will shatter. Don't do these things. I'm very clear. Do not do these things. Watch other people that know what they're doing do these things. But it's kind of some people call it instant freon, and that's kind of what that is. It's again, as you hold that can open for a long period of time, the remaining contents inside goes to a lower energy state. Some of it will liquefy, and you can use that cold liquid if you're safe and careful. And I'm telling you, don't do it to do things, right? So, but we're not gonna think about that scenario any more than I've just talked about. We're gonna say, how about if I just take that can and I use it like it's intended? I just spray and I quit, and I spray it some more, and then I quit. Over a very short period of time, you can assume uniform flow. Over a very short period of time, for like just a second or two, the rate at which that mass is going to leave the can is approximately constant. The energy that's dropping as a result of that mass leaving the can is reasonably constant, and the properties of the gas coming out of the can for a short burst are reasonably constant. And so we can make the uniform flow approximation, right? And what I'm doing here, if we go back and look at the differential forms of these, what I'm doing now is I'm saying for uniform flow, I'm going to approximate these as delta E system, delta T. And the same thing for the mass, delta M system, delta T. And so with that approximation in place, then basically if you've had differential equations, all we're really doing here is we're separating and integrating. All right, we're treating this as a separable equation. So I'm basically moving dt to the other side now of the equation. And if these are constant, I integrate these with respect to dt. Well, if these guys are constant, then this just becomes these guys times delta t, the rates times the amount of time. If I take a rate times the amount of time, put them together, that gives me the amount. Just like speed times time gives me distance, speed being the distance rate. Here I'm saying if I take the energy rates multiplied by time, I just get the amount of energy, right? Same thing with the mass. If I take the mass rate times time, I get the amount of mass. And that's all we're saying here. So we move the delta T over the other side of the equation, multiply it by the rates. That gives us the total energy change for the system. Same thing with the mass. Okay. So that's what we're going to do. That is a method we can use to solve unsteady flow problems, is over a very short period of time, we can make the assumption that we're dealing with uniform flow characteristics, and then we can treat these as these differentials as deltas, and this problem becomes solvable without a whole lot of differential equations knowledge, right? And that brings us to an example. So we'll work the example out in the next video. And that's very close to a 15-minute video, so hey, I'll take the win today. I'm going to stop recording. We'll pick up with an example problem.